Sometimes I just walk around among flowers and trees and plants. It clears my mind and makes me more calm. I just sort of let my thoughts wander and think about whatever comes to my mind. Mathematics is a way for me to understand the world. It's something that I could try to think very hard and understand from the axioms and the basics. What I understand, what I don't understand, and what needs to be understood. The first math problem that I was interested in was when I was 5 or 6. If you have 7 points in the plane, and then if 3 points in a row, and how many rows can you find? I feel quite happy when I figure out the answer. I feel like I have a clearer understanding of the subject. My parents gave me a lot of freedom to do whatever I want. They allowed me to go to bookstores and pick some interesting math books and try to solve the problems. My mom tried to teach me English, and my dad is a teacher in mathematics. When I went to college, suddenly mathematics became difficult. It took effort and discipline to actually learn it, and it took me many years. I felt a little discouraged, and I did an internship in architecture in Paris. After this internship, I decided that I should spend my most creative years in mathematics, and if it didn't work out, then I would reevaluate my choice after 5 years. After that, I stopped worrying about whether I'm good at math or not. I work in Fourier analysis and geometric measure theory. We see fractal sets in our daily life. For example, the snowflake, if you keep zooming in, then you see like some structures that are quite similar to the bigger structure. In some of the math problems that we work on, the structures are so natural that it felt that they have been there waiting for us to discover for a long time. I am a professor of mathematics at NYU Koran Institute of Mathematical Sciences and a permanent professor at the IHES. During COVID, I ran into Tao's blog posts on the Kakeya set conjecture. We decided to try to write down some details of this outline in the very special case of sticky Kakeya sets. So we have to spend a long time to overcome this. And in the end, we were more convinced that this is going to be solved. In 1917, Kakeya asked the following question. If we rotate the needle in 180 degrees, what is the smallest area it sweeps out? Surprisingly, Besekovich showed 2 years after, in 1919, that there exists a way of rotating the needle in 180 degrees such that the area it sweeps out is as small as you want. Besekovich's example showed that this set could have zero volume or zero area. A Kakeya set is a set that contains a unit line segment in every direction. The question is how small a Kakeya set could be. The Kakeya set conjecture states that any Kakeya set should have maximal dimension. Joined with George Zhao, we showed that any Kakeya set in the three-dimensional space has dimension 3. If there exists a counterexample to the Kakeya set conjecture in higher dimensions, then some functions, for example the solutions to the linear Schrödinger equation, might be surprisingly large. Another conjecture is about Furstenberg sets, which are more general than Kakeya sets. So instead of containing a unit line segment in every direction, it contains subsets of unit line segment of fixed dimension in any direction. In New York, there is a beautiful botanical garden. The greenhouse is very humid. It reminds me of the climate of Guilin. Every time when I come back home, I feel rejuvenated, and often I will go for a walk with my parents in the park. Guilin is a very beautiful and relaxed city. Sometimes it's nice to explore other things than math.